Did you hit the, is it recording? Oh, okay. I'll begin with a word of prayer. Dear Heavenly Father, we thank you for this day. We have to meet together and study your creation, Lord. I just thank you for all your many blessings to us this day, Lord. Pray that you'd just be glorified in what we do this day, Lord. In your name I pray. Amen. So you guys have questions? I was going to say, here's an idea. I've always tried to put this problem on a test, but I haven't really made it interesting yet. It's something I've been trying to do, though. Like the question goes something like this. So let S be the cylinder with top, but open base, and so in particular I wanted to orient it like this. All right, make sense? And the question goes something like this, you know, given F, right, calculate the flux of F through S. And we could be more specific. Let's suppose that the cylinder in particular is like, suppose this is R is equal to 3, and let's let the top of the cylinder be Z equals to 4, whatever, right? And let's let the vector field F be, I don't know, x squared plus y squared plus z z yeah, and then I don't know, yz, and how about xy plus 7? Sure, why not? So I think we can all appreciate why we don't want to do this calculation directly, right? What would you have to do? You'd have to calculate, I mean, direct calculation would look something like this. What? Something like the integral over S side. You'd have to do F dot, basically, what is it? It's 3 R hat dz d theta, something like that. This is a ds for the side, right? And then plus the integral over the top, which would be z equals to 4 and 0 less than or equal to r less than or equal to 3 in cylindrical coordinates. And then like the top would be f dot, what's the ds for the top? Well, ds for the top is easy enough. It's just r dr d theta z hat. You know, it's not too bad. But anyway, it'd still be a kind of a pain to actually do these integrals directly. Agree? Now, so how can we somehow figure out what the sum of these two integrals is without actually doing them? Well, here's the idea. If you look at the whole cylinder and close the bottom, right? So let's call this the base, if you like, or the bottom, and here's the top, right? And this is the side. Of course, that's the boundary of the solid cylinder, right? Let me give this thing a name. Let's call it E. So, and of course, so in other words, if I throw in this extra piece right here, right, and orient it downward to give the boundary of the solid cylinder the outward orientation, right? So this would be ds for the base. That's the surface area element there. I can use the divergence theorem. You know, what does the divergence theorem say? It says that the flux over the boundary of E of f dot ds is equal to the triple integral over E itself of the divergence of f. So let's call this flux phi. Phi is what I'm actually interested in. So what you have here then is you've got the flux you're actually interested in plus what? Plus the integral over the base of f dot ds, right, is equal to the triple integral over the solid cylinder of what's the divergence of f? Differentiate this with respect to x, what do you get? Differentiate that with respect to y, what do you get? Thank you. Differentiate this with respect to z, you get 0. So we just have to integrate 2x plus z over the cylinder. Now that we can do without too much difficulty, right? Because that's nothing more than the integral from 0 to 2 pi, the integral from 0 to 3, the integral from 0 to 4. Now I got to put my cylindrical coordinates, right? So x is what? R cosine theta. My z is, well, that substitution's easier. It's z. And then dv is r. And then what order do I put the differentials in? dz, dr, d theta. Very good. Now, we don't need to toil and labor much over this term because we know that the cosine theta will integrate to 0 because we're integrating over a whole cycle. And there's no theta dependence in the r and z, right? The integrals would multiply. And so all we really have to calculate then is 2 pi from the theta integral, and then the integral from 0 to 3 of r dr, integral from 0 to 4 of z dz. Which is 2 pi times 9 over 2 times 16 over 2, which is what? Nine pi times 8, right? Also known as 72 pi. Now that's not what we're after, right? That's not what we're after. We're not done yet. We still have something to do. We need to calculate this piece, right? So how do we do that? The integral over the base so that's the integral. Again, the region there is, let's say, 0 less than or equal to x squared plus y squared less than or equal to 9. And we have set z equals to what there? Z is equal to 0. And we're looking at the vector field x squared plus y squared plus z, comma yz, comma xy plus 7, dotted with the ds. Now what's ds? ds on the bottom is, well, it's 0, 0, minus 1 dx dy. See, this is minus z hat dx dy. Now, of course, I'm just doing this. I mean, I could have gone to cylindrical coordinates already, whatever. Of course, there are some really nice features about this vector field. On purpose, I did this. 0, this piece 0, right? And so what do you have? You have, oh, and in fact, it even doesn't matter what you put there because only the z component contributes to this flux. I could have put other awful things over here, wouldn't have changed the calculation. We have then the integral. Finally. It's taking me a semester. All right, integral from 0 to 2 pi. Integral from 0 to 3. And what do we have here? We've got xy, which is what? R cosine theta, R sine theta, right? Plus 7, big bracket. Dx dy, there's a minus. I pull it out. Pull this minus over to there. And then the dx dy is r, which comes first, dr d theta. Looks like the dr comes first, dr d theta in my. And what's this? Well, minus the integral from 0 to 2 pi, integral from 0 to 3. And let me just simplify this a little bit. This is r cubed, and that is 1/2 sine of 2 theta, plus 7r dr d theta. Good news, folks. Sine of 2 theta has period pi. So we're taking an integral of sine of 2 theta over 2 full cycles. So the positive and negative balance out. This integral goes to 0. And so this is the only non-trivial piece to worry about. And there's no theta dependence. The theta just integrates to minus 2 pi, with a minus out there, right? Minus 2 pi. And then 7 times r squared over 2, evaluated from 0 to 3. So the 2's cancel, and I'm left with minus 72 pi. Maybe not. Let's see here, the 2's cancel, minus 7 pi times what? Times 9. What's 7 times 9? Minus 63, right? So therefore, put it all together. What we got? We've got the thing we're interested in, the flux through the open cylinder, phi, minus 63 pi equals 72 pi. So therefore, the flux through the open cylinder is equal to 135 pi. Yeah. Yeah, it's a lot of pi. It's just a season for it, right?
After last Thursday.
Not after last Thursday. Yes. I think in principle those double integrals can be, there's got to be examples where those double integrals are prohibitively difficult to calculate, but this is easier, and vice versa. So it's just it's another tool in our toolkit. But it's a useful way of thinking. It's kind of a next order application, if you will, of divergence theorem. It's another thing we can do with it. You can play similar games with the curl. I mean, the principal application we have for the curl is something like, in terms of using the curl and Stokes theorem is like, if I have, this, and I have that, if I have the curl of a vector field is equal to 0 in between these, so C1 and C2, right? So I can think about, the ds vector being like this. So in other words, this is some surface, right? And if I have that the curl of f is 0 between these two curves, then I get that the integral over the boundary of the surface of f dot dr is equal to the double integral over the surface of the curl of f dot ds, right? But that being 0 implies that the integral over, let's see here. If I'm walking along, so it's minus C2 union with C1 if I'm walking along here. So C1 is positively oriented with respect to that choice of normal, whereas C2 is the opposite orientation to the natural orientation induced from the surface. And so this is the boundary of S is minus C2 plus C1. And so you have this is equal to 0, but that says that the integral over C2 of f dot dr is equal to the integral over C1 of f dot dr, which is a step or two more past what I wrote. So that's a deformation. There's a deformation theorem. But in principle, you could even imagine cases where you wanted the, you wanted the flux, so you wanted the circulation of the vector field around the outer edge, but it was easier to calculate around the inner edge and to actually do the surface integral of a non-trivial curl to adjust for how much extra circulation there was from that curl being non-trivial between the curves. Like, you could think about problems like that. That's a second generation homework problem, right? That's not what I think I've really given you. There may be one challenge problem in your homework like that, but. Oh, I just posted quiz 4. I don't know if you guys got the announcement or not, right? Yeah. Quiz 4 and solutions there. That kind of gives you some kind of sense of what the test will be like next Tuesday. So. Anyway, are there questions about homework? Yeah.
It's actually more about the subject matter than the homework itself. I might have spaced. This kind of goes to what exactly ds is, ds vector. I noticed there's a strong connection between ds and the Jacobian, at least on the standard examples. Is there anything to that?
What is the connection between ds and the Jacobian? Now, the Jacobian of what?
For example, a sphere, the ds is r squared sine phi.
Let me just put it up here. So for a sphere, you have noticed that ds was what? It was r squared sine phi d what? D phi d theta, is that right? Whereas, what was it? And what was that related to, you thought?
The Jacobian of a sphere is...
Oh, you mean the Jacobian in spherical coordinates?
Yeah, sorry.
That's fine. It's rho squared sine phi d rho d phi d theta. Huh.
Cylindrical coordinates r d theta d u.
So there, you're like, so that, and then so for, Well, let's think about, yeah, you could also go to the train of cylindrical, so cylindrical coordinates, you're thinking like for a cylinder, we have ds is r d theta dz, right? Whereas the volume element for cylindrical coordinates was, what was it? It was r dr d theta dz, right? You think there's some kind of pattern here, right? No, I think you might be onto something. I think you might be right. I think there might be some pattern here. Let's see here. Based on Luke's hunch that there is some pattern, let's see if we can see what the pattern is and guess from our conjecture of what the pattern is what the surface area element should be for like something else based on spherical coordinates. How about a cone? So it looks like what we did to get from here to here was to freeze rho to be r and to drop the d rho. So if there's any justice, right, we should hope maybe to get from this to phi equals to phi naught, aka cone, right? What should ds be for the cone? I guess we'd suspect it would be rho squared, right? Sine phi naught, yeah. And d rho d theta, right? Or what else could we try? We could try theta equals to theta naught, right? A half plane. That we'd think maybe ds would be what for that? You say d rho d phi? Is this, I don't remember off the top of my head. Is that the surface area element for a cylinder, for a cone? I worked it out in the notes, no?
If I recopied it right, it's not. The surface, or the ds for a cone is rho sine v naught d theta d phi.
So the order of the d theta and phi, so here's the actual. This is the real ds. We calculated it. Looks like we had an extra rho squared, huh? Yeah, so I think if we need to look at, you have to look at dv in the proper way. So we have to reinterpret, like dv, we should look at it like this. It's rho sine phi d theta times rho d phi times d rho. These have the proper units. I don't know if you can see this or not, but this is r d theta. So that's what I have to make go away. You see, and so to get from this to that, I have to drop the, I have to, it erases a copy of rho as well. So I have to like drop off the rho d phi, and it leaves me this and that. So if I'm right, then this wouldn't be right. I should drop off the what? Right, I should, and the sine phi as well. because the RD, like this is the theta piece. So that piece has to drop out. That actually, I mean, maybe you can't see it, but on the half plane, if you go like here, take this point, swing down like this, so a little piece like this will be rho d phi, and a little piece like this will be the d rho. So that makes sense. But there actually is something to this pattern, and this can be generalized to higher dimensions. What we're doing is we're taking the volume form, and we're looking at the induced volume form on the, I mean, dV with the proper understanding is a volume element for 3 dimensions. And we're looking at surfaces which are submanifolds of that. And so if we pull back the volume form to an area form, there's a way we have to do that in the proper way, and the proper way is to take the hook of the volume form with the appropriate differential, which is vanishing on the submanifold. But anyway, that is advanced calculus. Yes. I don't know. I think we can see it just by pattern matching here, at least. Yeah. You can do much by just thinking about the infinitesimal lengths in like each direction. I've heard from some engineering students, you guys are doing something like that in your statics course? Maybe not you guys. Anybody taking statics right now? Do you guys do anything about calculating moments of inertia by like finding infinitesimal lengths along certain curvilinear directions and integrating them? That's the same ball of wax here. I shut up. Are there any questions about homework?
I'm having trouble visualizing surfaces for one thing and one about.
Aren't you thankful we just have to we really just have to visualize the surfaces. We don't have to visualize the vector fields. Isn't that freeing? Yeah. Although maybe there is something to be gained in thinking about how to visualize the vector fields in certain cases. Let's look at 110. You have z equal to 4 minus y squared. Yeah.
Yeah.
And x equals to 0. X equals to 1, z equals to 0. All right, so if we draw like the z, y plane, right? This is a parabola which opens down with z-intercept 4. Right? But z equals 0 is in the game, right? So z equals to 0 is this guy. So basically it stops it here and here, right? So we can ignore that part of the parabola. Then this is repeated at each x slice. I mean, I could put x equals to x naught, and this would be valid. And that just repeats from 0 out to 1.
All right. So it's pretty much just a wedge you can go cut out of the top of the saddle.
Yeah, I think it's like a, well, yeah, something like that. If I haven't messed up something, this is z, this is y. Here's x. Did I do that wrong? I said assume the orientation of the surface is outward, away from the x-axis. Does that make sense now that we've drawn this?
Yeah.
So the normal vector field is like this, right? What's the parameters? I mean, how do we actually set up? So what's the parameterization here? What would you do? I would use x of, what would I choose as parameters here? I think x is a nice choice of parameter, perhaps. Not even looking at the vector field. I mean, parameterization is always an art form. But here's, without thinking too deeply about it, what I do. X and y. So those are easy enough. X goes to x, y goes to y, right? And what's the z? 4 minus y squared. This is a graph. So we already know what the song and dance is going to be. We know partial x cross partial x, partial y works out to minus fx minus f. Oh, wait a minute. No. That's not right. This, right? Right. If you're not sure, work it back out again, right? But for this problem, that's what? So the ds actually is 1, 1, so this is my f, right, my graph. So I just have minus a minus, I get 2y, right? So the ds, but I think you already knew, Luke, that ds is, like, formulaically, it's the normal vector, the magnitude of the normal vector times du dv. In this case, it's the normal vector times dx dy, because x is u and y is v for our current thing here. Is that right? It feels wrong. No. Something wrong here, guys. The normal should not have any kind of x component. Unless I'm visualizing this wrong. I mean, this trough, it doesn't, the normal should be, it shouldn't have an x component, right? Just look at it. Oh, yeah, I mean, there is an x involved. I'm just saying that unless I'm looking.
All the x does is tell you where the normal is.
Right, but what I'm saying is that there shouldn't be a x component to the normal. The normal should be. Right. Okay, I must be, the devil's in the details that I haven't worked out today, right? So what is this? Fine. Yeah, okay. Okay. Yeah, you're right. I was trying to save work, and as you can see, usually my plans to save work are ill-founded.
In other words, laziness is disaster?
Yes, pretty much. Laziness is its own reward. Let's see here. Well, the last one is 1. Ah. Okay. That's better.
0 minus 2y, sorry. Positive 2y.
Now that makes sense, right? The normal vector, so the ds is something like 0, 2y, 1, dx dy. Now that makes sense to me, right? The y points a little bit in the y direction when y is positive. It points in the minus y direction when y is negative. It's always pointing up, and there's no x component to it. That's better. Does that help? I know your question is mostly just about how to visualize the surface, but
Also 111.
111?
It's a conical
Conical frustum. Z equals to
It's so frustrating.
square root of x squared plus y squared, yes. It could be. You know, there's a somewhat famous mathematician who died by walking off the top of one of those step pyramids. It's true. Oh, sorry, that's kind of like this is sort of like a frustrum, generally speaking, is like you just, you have like a pyramid but cut it off or something like that. I mean, these sort of things are...
So conical frustum is just a cone and it's pointy bit.
Yeah, pretty much. It's, so this, without anything else in the way, this is a 45-degree cone. This is in spherical coordinates, also known as phi equals to pi over 4. But it's been z equal to 1 and z equal to 2. So all we're left with is this bit. And then back here, right?
That's the same figure as in column 9.
Yeah, yes, it is. That is exactly the same surface. Well, that is very... I'm sorry, I should have given you different surfaces and different problems. This is not... I'm not... Do not tell the diversity officer about this. I am failing to be diverse in my homework. Yeah. Man, it has been a big week in peaceful Islam news, I tell you that. What's that?
Diversity officer is only at public schools.
Oh, okay. We have no diversity officer? No. Now, does that... What was your question, though? Just...
Just wondering because, yeah.
Okay, so then once you have that, it's one of our standard examples. So basically, this is a sub-piece of a cone. So we can use ds vector as, like, apparently rho over the square root of 2 d rho d theta. And the direction of it actually is phi hat. Phi hat points like this.
Oh, yeah, yeah.
Now, of course, for the problem you have here, that's not super helpful because you actually need the details of phi hat, right? Which I'm not so confident I remember off the top of my head. Like rho hat I can do, because that's just spherical coordinates with the rho peeled off. And I know that phi hat is perpendicular to rho hat, and I know the theta hat. So can we figure it out by process of elimination? So here's your theta hat. Here's your rho hat. Phi hat has to be perpendicular to both of these guys. What is it?
Cross product of the two?
Exactly. In fact, it is the cross product of the two. Now, to visualize that properly, which one is it, though? So here, rho hat looks like what? Rho hat looks like this. And phi hat is mighty difficult. I mean, theta hat's difficult to picture. It's coming out of the board here, right? So let's see here. Phi hat. Looks like I think I need to do theta hat crossed into rho hat. Theta hat cross rho hat should be phi hat. Likewise, rho hat cross phi hat gives me theta hat, and also phi hat cross theta hat gives me rho hat. By the way, that's why I write the coordinates rho phi theta when I'm when I'm thinking carefully, because that's their order to make them a right-handed coordinate system. In the same way x, y, z is a right-handed coordinate system. Anyway, so you say just take the cross product of what and what? Apparently. Oh, so so we're lucky. I wrote them in the right order. So to get the x component, I do this, right? So I get cosine theta, cosine phi, and then what the y component is sine theta, cosine phi. Z component is I don't remember that. Okay, fine. It's got sine cosine, doesn't it? So minus sine theta cosine. Is that right? Sine theta cosine theta. I feel like I made a mistake somewhere. We can check this in my notes, though, right? Did you check it, Zach?
No, that's okay. I don't remember. I couldn't find it. It wasn't here, or I wasn't looking at the right.
Oh, okay. I saw you looking at something. I thought maybe you were looking it up, but
That's what I was looking for.
yeah.
Oh, okay. Yeah, that's like the first term of the z code. But we need to do the second term of the theta, second term, like the first term of the phi to get.
Oh, there's two of them? Is that it? That doesn't feel right to me. I mean, is that a unit vector? I don't know. It's not a unit vector. That's not right. Is my theta hat right?
Yeah, there's no up and down to theta.
Yeah. But there's a sign choice. SIGN. Is it sine theta minus cosine theta?
No, rho hat is cosine theta sine theta.
Oh, goodness gracious, thank you. I am such an idiot. Duh. Golly, I can't believe I did that. Yes, the cosine is first for the x, and the sine theta is for the y, of course. Duh. Goodness gracious. Take away my license to do multivariate calculus. Actually, just analytic geometry. So what happens? Sorry about that. So then the x is what? Cosine phi, cosine theta. And then the y is what? Negative sine theta. Did I hear objection? I like it. I should say if you think something's wrong, you should say like objection. Professor is badgering. I'm sorry. Sine squared, cosine squared. Oh yeah. Now we got ourselves a minus sine phi. Woo. Yeah. That feels better. Second one's positive? Okay. Of course, we could take the dot product and check pretty quickly that that has to be plus plus in order to get the minus plus cancellation to get dot product to be 0. Anyway, so that actually is. Now, for the cone that you guys are looking at in this particular problem, cosine phi is what? It's 1 over the square root of 2. 1 over the square root of 2. 1 over the square root of 2. I mean, that's actually the phi hat on your cone, because you got the pi over 4 cone. Which one? Which, there's so many second terms. This one? Oh, yes, thank you. I think the lesson we've learned from this is that I should look up my formula in the notes. I do think it's healthy for you guys to realize that you can work these things out. If you understand their interrelation, if you understand, the more interrelations you understand, the more you don't have to remember. Well, guys, any other questions? I think we can end early today. I hope is it early? Yeah, it's early. Let's call it a day. Tomorrow, I have something interesting to show you after you give me your mission. Yes? No, it's not a bad thing. I already, those are already posted.